Good morning, everyone. My name is Tom Reed. I am with Catalyst Connection, and we are the managing partner of the AIM Higher Consortium. The important information is what you're going to hear from Mike, and so anybody who's a minute or two late will be able to catch up. But again, my name is Tom Reed. I work for Catalyst Connection, and Catalyst Connection is one of the partners who support the AIM Higher Consortium, and we are a group that are focused on helping manufacturers, small, medium-sized manufacturers in southwestern Pennsylvania and the state of West Virginia to find opportunities within the defense supply chain, and especially through helping them to advance technology through projects and needs to advance technology. This is what you're watching. The webinar you're watching is part of our AIM2Learn series. So you can learn more about the AIM Higher Consortium and this series of webinars at aimhigherconsortium.org. There you can see all of the partners who work on this. You can see a lot of the resources. We have a directory there, a database of manufacturers with capabilities as well as the partners. You can look at a map and sort out by specific needs to see kind of who is a part of this region and some of the capabilities. So again, bottom line is I encourage you to go to aimhigherconsortium.org after listening to this. Many of the webinars that we host are recorded and made available on the website. So if you want to go back and look at past topics, if the recording is there, you are welcome to view it, share it, that sort of thing. It's all public information that's on the website. So today, this is, I believe, our 14th AIM2Learn webinar, and I'm excited to introduce you to Mike Pollock. He's the Senior Director of Advanced Engineering and Manufacturing at Concurrent Technologies Corporation. CTC is one of the AIM Higher partners, and we're excited to have him talk about Friction Stir Welding. So welcome, Mike.
Tom, thank you very much for the introduction. So I am a Senior Director of Advanced Engineering and Manufacturing at Concurrent Technologies Corporation. And most of my focus, I'm a mechanical engineer by profession, but have moved into the application engineering and business development and trying to help companies adopt the friction stir welding technology. The reason we do that, CTC is a nonprofit applied research and development firm with a lot of focus on application engineering, and specifically in advanced materials and manufacturing technologies. And so we help the DoD and industry apply new manufacturing and material solutions to their products and help transition that into full rate production type of applications. CTC's segment, in the DoD, we probably are doing 80% of our work comes from DoD funded activities, either directly with the DoD or for OEMs that work in the DoD market space. The remaining of that is in support of OEMs in the commercial sector. So I am going to talk to you guys today about the friction stir welding and how we can help educate on the technology and help industry transition it into their portfolio of offerings. But before I jump into that, I do want to thank the AIM Higher, to allow me to brief industry through the AIM2Learn series. So thanks very much to those folks. All right. So just on the agenda side, we're going to go over a little bit of a technical overview of the friction stir welding. I'll give you a little bit of history of it, exposure to some of the market sectors and their influence on the technology, and then how we can help you with technology transition. So you're probably all familiar with traditional welding technologies where you have a high current that generates an arc You have a filler material that's introduced into the arc. You have a substrate base material that you want to join together. And basically it generates a molten pool of material that solidifies and joins the parts together. That is known traditionally as fusion type of welding, and there's many different forms of that. The most known are the tungsten inert gas or TIG welding, or the metal inert gas, the MIG welding practices. The solid state welding, friction stir welding, is quite a deviation from that, in that there is no filler material traditionally. There's no additional heat input from some electrical means applied to the joint. It is done through pure pressure and force applied to a rotating tool in a machine that is plunged into the material, and it generates the frictional heat that basically plasticizes the material. It does not create a melt pool. So the energy in the weld region is much lower than traditional fusion welding, and so there's some benefits that you can get from it. From a metallurgist standpoint or material science standpoint, the material is remaining in the solidus phase, so you're not considered melting it, and so there's some advantages that can be gained from that. Friction stir welding was identified and patented around 1991 by the Welding Institute out of Cambridge, England. Around 1998, CTC got involved with it and started paying licensing fees to the Welding Institute so that we could do research and development for the U.S. Defense Department. And we've been working in that field ever since. I'm going to try to show a video here, but if you look at the picture on the right of the screen, that is a rotating tool being forced into the material, and you can see that's an aluminum application. You can see the material to begin to ooze out. That'll continue to happen until the larger diameter shoulder makes contact with the parent material. At that point, it'll contain it and keep all the forging forces within the weld region. So let me try to do a video here. So here's a quad video of some different tooling, different applications performing friction stir welding. It's very diverse. There's traditional tools that you see in the top left where you have a single probe penetrated into the material, rotating and doing a full penetration weld. And then in the lower right corner, that is a self-reacting tool or a bobbin tool that has a shoulder on each side of it. So both of them have their benefits in particular applications. Both make a very homogeneous weld in the material. CTC does develop customized equipment at times. The lower left picture is an application for naval vessel repair, where we developed a man-portable friction stir welder that can go right into the shipyards to help mitigate cracks and things that occur in aluminum ship hulls. So we do a lot of work in the research side, even at the equipment level, but also process optimization. Over the years, we have probably built all the advanced technology demonstrators for the U.S. Army, and we'll get into some of that in the future slides here. So why would you adopt the technology of friction stir welding? Well, when you get into thick materials, such as what ship hulls or combat vehicles be made from, there's quite a savings in the manufacturing cost. It is much faster to apply this technology than using conventional welding, even if you apply robotics to conventional welding. The equipment is capable of doing single pass welds up to 4 inches thick. And so that would take hundreds of fusion passes to join something together that thick. And friction stir welding can offer that in a single pass. There's much less energy involved, so there's some beneficial features that come from that, in that your distortion is much lower. Defects are, because it is buried into the weld region, the defect propensity for defects is much lower than fusion welding. And it doesn't take so much workforce skill set to apply the technology, because it is pretty much a process that is machine controlled, computer controlled as well. There are some cons to it. You know, when you get into the computer controls, you probably are familiar with you know, 3-axis, 5-axis machining centers. So friction stir welding is no different. It's limited to the application of how you can maneuver the tool through the part. So very complex parts become more difficult to apply the friction stir welding to. So that's something to keep in mind when we're trying to look at how well we can adapt this technology to a product. Some of the other things that come forward in it, it allows you to, friction stir welding, you can apply some of the advanced high performance alloys in a 2000 series and 7000 series that don't lean towards fusion welding. Very difficult to fusion welding, if not impractical altogether. The friction stir welding, being that it's solid state, allows you to join those materials together and provide a very robust joint. This is not just in aluminums. This could be applied to coppers, titaniums, stainless steels, and so forth. But in the aluminums, the joint efficiency is typically, you know, much higher than a fusion weld, upwards of 33% higher strength in ultimate tensile strength of the welded joint. And we can see elongation improvements up to 200% over fusion welding. So that's where, you know, industry is really, the ones that have adopted it, they've adopted for reasons of lightweighting, high strength, and the manufacturing time reduction that's associated with the process. Also just want to point out, from an equipment requirement, you know, anything in the aluminum series that's 1/8 inch to 3/8 inch thick can be done on traditional CNC mills. We do that frequently at our facility and help our customers that are looking to adopt a technology. Many of them have the machining capabilities and then are able to realize the welding capabilities of utilizing that equipment. Anything beyond the 3/8 to, you know, maybe stretching it to 1/2 inch, anything beyond that, the machines typically become very specialized for the friction stir welding process, because the forces are beyond what a traditional CNC mill can handle. Some of the history here, some of the early applications, you know, Boeing adopted this for the Delta rocket fuel tanks back in the late 90s. The space shuttle external stores tank, fuel stores tank, was adopted for friction stir welding in the early 2000s, as well as Eclipse Aviation gained FAA approval to apply it to airframe structures in the early 2000 timeframe. Almost in all these cases, what they were looking for was the benefits of some new advanced alloys of aluminum, namely the aluminum lithium alloys that could not be fusion welded. And so the friction stir welding was able to bring that material, that high strength material, into the application for space and aerospace applications. Okay. CTC got involved around the early, late 1990s, 2000 timeframe. Some of our material scientists were also involved in space programs and bringing aluminum lithium materials to use in the space program. And they saw the immediate application for combat and tactical vehicles to, again, focus on lightweighting them, as well as improving survivability by bringing forward advanced high strength materials. And again, friction stir welding was the enabler to do that. So in the early 2000 timeframe, in conjunction with the former Tank and Automotive Command out of Warren, Michigan. CTC developed a large format friction stir welding machine capable to weld entire combat vehicle hulls. And set out in the early 2000s as well, applying that to the first one was the triple AV, double AV advancements for the Marine Corps amphibious assault vehicle, where some of the components were friction stir welded on that as a demonstrator. So if you look at the marketplace over the years, it continues to have a very good cumulative growth rate for the equipment. So we see a lot more equipment being acquired by industry as they apply it to their product lines. And so if you imagine following the suit of the equipment, the technology seems to be transitioning more and more at a similar growth rate to what the equipment sales are. So, there was a 5.5% CAGR from 2016 through 2021, and it's expected to grow at a rate of over 7% from 2022 to 2027. So pretty aggressive growth rate in the market. If you look at it by sector, the automotive industry with electric vehicles coming to line is using friction stir welding more and more, again, for lightweighting of the automotive frames. Also battery boxes, heat exchangers, all those have applications in the automotive industry. As you see more companies, SpaceX, Blue Origin, and so forth, getting involved in the aerospace and space market, you see quite a use of friction stir welding there as well. Railways use it again for lightweighting and some of the manufacturing, speed that you can produce parts with friction stir welding compared to fusion welding, and the lower distortion are the driving forces why the rail industry is interested in this technology. Ship and boat market also growing. This has been utilized by the U.S. Navy for some of its assets over the years, but we see more and more of the OEMs that build smaller craft are also adopting the technology because of the quality enhancements and the lower distortion rates, higher throughput that you can experience with the technology. So if you look at the full life cycle of the technology, CTC does work the full gamut. So from requirements definition, design development, prototyping and testing, and aiding in production readiness. Here's two examples recently we've done in working with the U.S. Army and the U.S. Marine Corps to allow us to build combat vehicle hulls and do demonstration of the technology so that both of those agencies can set requirements for the acquisition of their programs. Namely, for the one on the left is for the optionally manned fighting vehicle, and the one on the right is for the armored reconnaissance vehicle. Some other industry that we help support technology transition in, design and development, prototyping, and production transition would be into semiconductors. We have OEM that we support there to transition the technology into their product line. Ships and boats, we're supporting OEMs there to produce panels and hull structures for Mark VI patrol boat. And we have some customers we're working with to apply the technology to cryogenic domes in support of all the OEMs that build spacecraft. So how do we do that? CTC has a lot of experience in if you look at the left side there, all those areas are what's required to really apply the technology to a product. And we offer the full gamut of services, to help industry apply the technology to a product. And so from engineering to technician experience, we're very keen on that and able to focus those areas to transition to technology. This just gives you an overview, just real quick, of some of the resources we have. So from a material science perspective, for process optimization, we have PhD scientists on staff that really understand the process and how it applies to specific materials. You know, application engineers that can design tooling, fixturing, the full gamut to help the customer in setting up the production line. We also do a lot of advanced technologies, working with the DoD and applying new control algorithms, new sensors to the process. So we're constantly trying to improve the ability to adopt the technology by industry by advancing the machine learning aspect of it. So I'm running close on time here, so I'm just going to at this point open it up to any questions. Again, certainly, you know, wanted to educate you all on what the technology is. Hope I was able to accomplish that. If you are involved in welding and or machining, certainly if you see applications for your customers, we can help you transition that technology.
Okay. Yeah, and I think the way that our the way this is set up is you would need to type in your questions in the questions section there over to the right. And I know we did get a couple of questions already, Mike, so I'll kind of share those with you and you can answer the group, but feel free, anyone who wants to go over there and type a question and we'll cover those. So here's the first one. What kind of defects are common with FSW, and are there countermeasures developed to prevent or minimize those defects?
Yeah, so there are defects that can be associated with the process, usually controlled very well once you understand what they are. I would say the biggest thing we see is understanding the tool life for a particular application. And what you wind up getting is when the tool wear becomes too extensive, you'll start seeing wormholes appear on what we would call the advancing side of the tool, very close to the surface of the material that you're welding in, or just slightly below the surface. And those, you know, when they're identified, they are something that can be repaired without, you know, too much challenge by simply re-stir welding it and reconsolidating the material. So there are defects, but they are defects that can be repaired fairly quickly.
Great. This was asked earlier, and so I don't know if Mike, if this makes sense. You know, I'm not sure at what point in the presentation they're referring to, but they just were saying what material or materials are used for the tool. I don't know.
Yeah,
if that...
so yeah, it depends on what alloy you're trying to weld. A lot of your tool steels can be utilized for it. H13, MP159, those work very well in aluminums. When you get into the higher strength materials, coppers and titaniums, that's where you start seeing a lot of the tungsten alloys, tungsten rhenium, tungsten hafnium, some synthetic diamond type of materials as well are utilized for those higher strength materials.
Great. Okay, so here's another question. So obviously, you know, as you were talking, CTC staff is highly educated and knowledgeable with friction stir welding. What are how high of a skill level is required for a general user in the FSW?
So, you know, we have customers that are using purely operators to weld their product. Once the equipment, the control algorithms and everything has been proved out, qualified, everything is dialed in, it does not take a high skill set to apply this technology. Traditional machine operators are capable of doing it just like you would have in a manufacturing environment. On the research side, that's where it becomes a little more requirement for skilled technicians that can understand the process and can communicate and relay information to the materials and engineering team so that we can get the right feedback to optimize the process. But once it's dialed in, traditional operators are skilled enough to apply this technology.
Great, and I guess this is kind of a follow-up question then about the tools and the equipment. So for a company who would be interested in adding this capability, are the tools commercially available today? I mean, can they be purchased?
There are some companies out there that, one of them that comes to mind is Megastir. Megastir's business was to provide tooling and process parameters to customers who want to adopt the technology. They were acquired by a company called Mazak, who builds CNC machines. And so they did that to provide a complete package to the customer, from the equipment and all the processing tooling required. We also can offer tooling designs. And I think some of the other machine builders, such as Bond Technologies, also offers tooling solutions to the customer. And then again, you always have the Welding Institute in the UK. They are also a source for tooling.
Great. Yeah, so I guess my recommendation would be for anyone listening who wants to know more information about how to access equipment and that sort of thing, they're welcome to reach out to Mark directly. You can reach out to me through the AIM Hire Consortium, and I certainly don't have the answers, but I'll put you in touch with Mark or someone, or with Mike or someone else who may have that information available. So if someone was looking for more of that offline after this presentation, feel free to reach out to us and we'll help put you on the right track as best we can. One more question about expertise, Mike. So the question is there adequate expertise among the testing laboratories to properly apply NDE for the friction stir welding parts?
So yeah, today CTC itself has capabilities to do non-destructive evaluation. The benchmark for friction stir welding is phased array ultrasound testing, but there are third parties that we utilize as well that you can bring in to do phased array and or radiographic X-ray inspection. Both of those are accepted as technologies for friction stir welding to do non-destructive evaluation. Our preference is the phased array. So to answer the question, yes, there's companies out there that can perform the inspection and understand the how to read that information.
Great. Well, fantastic. I believe those were all the questions that I see here. Mike, thank you so much for your time. Thank you for everyone who listened in and got some good information on the friction stir welding topic. If anyone has any questions, like I said, feel free to reach out through the aimhireconsortium.org website, or you can email or call us directly. I'm sure Mike would be willing to do a follow-up, answer a question if you have one. But beyond that, thank you all. And I believe our next Aim to Learn is 2 weeks from today. And let's see if I have it handy. The topic is robotic adhesive and sealant dispensing, addressing ongoing difficulties and problems of manual application. So for those of you who might be interested in that topic, feel free to sign up and join us 2 weeks from today. Okay, well, again, thanks, Mike. I appreciate all the information and your time, and we'll talk to everyone again soon.
Thank you.